In the vast theatre of the cosmos, where billions of stars are born and die in a never-ending cycle, mysteries abound at every turn. Among these, one stands out as perhaps the most profound and perplexing of all. Black holes stand as the universe's greatest enigmas, captivating the imagination of scientists and dreamers alike. These cosmic phenomena are not just objects of fascination, they are puzzles that challenge our very understanding of reality. They are not empty spaces, but regions where gravity is so intense that nothing, not even light, can escape their grasp. The boundary around them, known as the event horizon, marks the point of no return, a place where the known laws of physics break down. Imagine a predator so perfect, its hunting ground is the universe itself. Black holes consume everything that strays too close, from gas and dust to entire stars, leaving behind only questions and mysteries. Black holes are cosmic rule breakers, where the fabric of space and time is warped beyond recognition. Here, the familiar rules of physics collapse and the universe reveals its most secretive side. Our journey to understand these titans is one of humanity's greatest adventures, told through mathematics, the light of distant stars, and the relentless curiosity that drives us to explore the unknown. The discovery of black holes revealed a hidden, darker side to the cosmos, one of extreme forces, unimaginable densities, and profound questions that challenge the limits of our knowledge. They push the boundaries of human knowledge, reminding us how much we have yet to learn, and how much more there is to discover in the universe's endless expanse. The story of black holes is the story of our quest to understand the unknown, a journey that continues to inspire awe, wonder, and the unyielding pursuit of truth. One of the strangest and most mind-bending effects of a black hole is not just its immense gravity, but the way it twists and distorts the very fabric of time itself. This warping of time is a direct result of the black hole's powerful gravitational pull, which bends not only space, but also the flow of time. Near a black hole, time slows dramatically, a phenomenon called time dilation, predicted by Einstein's general relativity. The closer you get to the event horizon, the slower time moves for you compared to someone far away. Imagine watching a friend approach a black hole. From your perspective, their movements become sluggish, almost as if they're wading through invisible molasses. Their time crawls compared to yours, and every second for them could be minutes, hours, or even years for you. If they continued toward the center, moments for them could stretch into centuries for you. The difference becomes so extreme that, as they near the event horizon, time for them nearly stands still from your viewpoint. Should they ever return, they'd have aged only a little while you might have lived an entire lifetime. This isn't science fiction, it's a real consequence of the laws of physics. At the Singularity, the very center of the black hole, time itself halts completely. Here our understanding of physics collapses, and the rules we know no longer apply. The concept of before and after loses all meaning. Past, present, and future blur together in a way that defies human comprehension. Gravity's grip is so powerful it can freeze the very flow of existence, trapping light and time itself in its grasp. Black holes are not just objects in space, they are cosmic laboratories where time and space are twisted and stretched beyond recognition, challenging everything we think we know about reality. Here, at the edge of the unknown, the ticking of the clock is silenced forever, and time's strange dance comes to a standstill. Every black hole is surrounded by an invisible boundary, the event horizon. It's not a surface, but a point of no return, where gravity's pull becomes inescapable. Once crossed, nothing, not even light, can escape. The event horizon is a one-way door. You can enter, but never leave. From afar, it appears as a perfect sphere of darkness, a shadow against the stars. Its size, the Schwarzschild radius, depends on the black hole's mass. Watch someone fall in and you'd see them slow and fade, never quite crossing from your perspective. For them, the journey continues, but to us, they're lost forever. The event horizon marks the edge of the unknowable. Imagine crossing the event horizon in a spacecraft. There's no wall or signpost, just a subtle, inescapable pull. Inside, space and time swap roles. All paths lead to the singularity, as inevitable as tomorrow. You can't turn back. Moving away from the center is as impossible as reversing time. Looking back, you might see the universe's future flash by, as time outside rushes forward. The light from stars would be blue-shifted, compressed into a bright window, but soon tidal forces take over, ensuring nothing survives the trip to the center. The journey ends in destruction, a spectacular finale to a one-way voyage. The black hole's interior is a realm where destiny is absolute. Black holes are cosmic laboratories where our two greatest theories, general relativity and quantum mechanics, collide. General relativity explains gravity and the large-scale universe, predicting black holes and their immense pull. Quantum mechanics governs the tiny, unpredictable world of particles. At a black hole's singularity, both theories should apply, but they give contradictory answers. Relativity predicts infinite density. Quantum mechanics says infinities shouldn't exist. This clash is one of science's greatest unsolved problems. We're missing a unifying theory, quantum gravity, that can explain both the large and the small. Black holes highlight the limits of our knowledge and point toward a deeper understanding. They are not just destroyers, but signposts to new physics. Here, the seeds of a scientific revolution may lie waiting. The end of a journey into a black hole is spaghettification, an extreme stretching by tidal forces. As you approach, gravity pulls much harder on your feet than your head, stretching you into a thin strand. For small black holes, this happens before you reach the event horizon. You're torn apart and join the swirling disk of matter. For supermassive black holes, you might cross the event horizon intact, only to be stretched closer to the center. Spaghettification is the ultimate fate for anything falling in. It's a violent, fascinating process, matter drawn out and consumed by the singularity. The black hole's appetite is absolute. Black holes challenge a core principle of physics, the conservation of information. In theory, information about every particle should never be lost. But when something falls into a black hole, all details seem erased. Only mass, spin, and charge remain. This creates the information paradox. Does information vanish, or is it somehow preserved? Resolving this paradox is crucial for uniting quantum mechanics and gravity. Some theories suggest information is stored at the event horizon or leaks out as radiation. The puzzle remains unsolved, inspiring debate and new ideas. Black holes are cosmic cliffhangers, pushing the boundaries of what we know. For much of the 20th century, black holes were shrouded in mystery. They were once thought to be eternal prisons, regions of space where nothing, not even light, could escape their grasp. These cosmic enigmas were believed to swallow everything that crossed their event horizon, locking away matter and information forever. But in 1974, the brilliant physicist Stephen Hawking challenged this view and forever changed our understanding of black holes. Hawking proposed that black holes are not completely black. Instead, they emit a faint thermal radiation, now famously known as Hawking radiation, arising from quantum effects at the very edge of the event horizon. According to quantum theory, empty space is never truly empty. Virtual particles constantly pop in and out of existence in pairs. Near a black hole, one particle can fall in, while the other escapes into space, making it seem as if the black hole glows with a subtle, ghostly light that is almost impossible to detect. This radiation is incredibly weak for large black holes, but it carries away energy, causing the black hole to slowly lose mass and eventually evaporate over unimaginable timescales, trillions upon trillions of years. Hawking's discovery was revolutionary because it bridged the gap between general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the tiny world of particles. It hinted at a deeper, unified connection between the two great pillars of modern physics, a connection that scientists are still striving to fully understand. Hawking's work also offered a tantalizing clue to the infamous information paradox. The puzzle of whether information that falls into a black hole is lost forever or somehow escapes. Perhaps, he suggested, information could be encoded in the radiation itself. This sparked decades of debate and research as physicists around the world tried to unravel the mystery. Thanks to Hawking's insight, black holes are no longer seen as static, unchanging objects, but as dynamic, evolving entities that interact with the universe in subtle ways. They are not just cosmic takers, but also subtle givers, releasing energy and perhaps even information back into the cosmos. Today, black holes are at the heart of our quest to understand the fundamental laws of nature, inspiring new theories and experiments. No longer just cosmic endpoints, black holes are now seen as complex, fascinating systems, gateways to deeper truths about the universe itself. Black holes are more than cosmic curiosities. They are fundamental to our understanding of the universe. They mark the limits of our knowledge, where our theories break down and new discoveries await. Studying them forces us to confront the deepest questions about space, time, and reality. Each new observation brings us closer to unraveling their secrets. Black holes challenge us to think deeper and push science forward. The quest to understand them is ongoing, driven by curiosity and wonder. The universe is filled with mysteries, and black holes are among the greatest. The story of black holes is far from over. We have only begun to listen.